One of these is going to go in here, okay? But you have to keep it there.
Washington
So
18,
you have to hold it like this, without touching the metal, and then I will be able to do the rest of it. Okay? All right. Whenever you're ready.
I'm out.
You can do this.
I've already started.
Hi, this is T.H. Culhane for Porpoise Robotics at Washington Preparatory High School. And with Easy Money and with Luis Camacho and Chris Brandon behind the camera, we are now going to show how you test the current draw of these motors, because when we start running off of this Adafruit motor controller, we need to be careful not to overdrive it. Each of these chips, these H-bridge chips, can only draw 1.2 amps peak and 0.6 amps continuous. And after that, these will fry. They'll burst into flames. We've had it happen over at Venice High. So we're going to test this and see just how much this thing draws. And to do that, I take my multimeter and I turn it into an ammeter by taking the red lead and putting it where it says 10 amps, out of the one where it says V-ohm milliamp. We don't want milliamps, we want amps. So I plug that in here, I keep the black and calm, and I turn it on to amperage, and I'm going to put it at the 10 amp setting. And now what I'm going to do is, Lewis has the negative lead of one of the motors on the negative terminal of the battery. I'm going to take this positive lead and put it here on the positive. And now I'm going to touch the lead of the battery. You hear that the motor goes, and you look and see how much current it's drawing. See how it starts out? It's about 0.5, 0.49, 0.5, 0.49. When I start it, you'll notice it jumps up even up to an amp. It's 0.6, sometimes 0.7. So when a motor is starting, it's called an inductive motor, it needs a lot of current to start turning, to get that torque going, to overcome inertia, because things in motion tend to stay in motion, things at rest tend to stay in rest.
Unless acted on by an outside force.
Thank you, and that outside force is electricity, so it needs a push for that inductive motor, and it can jump up. It just jumped to 0.68. But because these bridges can handle up to 1.2 amps, we're safe. It can take the spike, it just went to 0.69, because then it settles down to 0.5, which is within the range. This generally operates continuously at 0.6. There's a problem, however. Easy, I need your help with this problem. What happens if it gets stuck in seaweed or if there's a tough current? And if you can hold the motor, we'll show what the peak load of current is when it gets stuck in seaweed. So Easy's going to grab the motor.
While it's going?
Yeah, just put your finger in. It's plastic. It won't hurt you. And notice it went up to 2, 2.09, 2.0, 1.9. Let go. Now it drops down to 0.43, which is safe for the motor. Do it again. Get it caught in seaweed. Gets caught in seaweed. And it goes up to 1.8, 1.9, and 2. And that is over the peak rating of 1.2. So if it got caught, as it did at Venice High when we were trying this, a kid had glued this to the plastic just a little too tight, it wouldn't turn, and this thing burst into flames. And we lost a chip and almost lost the board. So because of that, we are only going to use this board for testing, and then we're going to get different chips that can handle a higher amperage. They're a little more expensive, and we're going to replace these chips with higher amperage chips. But for now, for testing, because there isn't any seaweed or water, and nobody's going to stick their finger in, we can do, as you saw there, we can do this and get our tests going, because it only goes up to a little less than an amp and then settles into about 0.4, 0.5 amps. So that's the crucial thing to know about these particular motors. Before you do any of these robotic projects, test your motors. Find out what their continuous operation amperage is. Find out what their spike is when they start, that inductive spike when it kicks in, and then find what the stall is when it gets caught, and see just how much current it draws. And as you saw, it can draw up to 2 amps, and that would fry a chip that only uses 1.2. One other technique we're going to show a little later is how you can piggyback a second one of these chips. If you can't find a more powerful chip, you can put another chip on top and solder it down and double the current capacity. It's not the best solution, but in a pinch, if you can't find other chips, stacking one on top of another does give you more current flexibility. Thanks.